If you size your solar charge controller the wrong way, you risk having a system that wastes energy, or in the worst case, you risk damaging the controller itself. But it's not about picking the biggest or most expensive controller you can find, because that usually ends up being overkill and a waste of money. The proper way is actually an easy and simple two-step process. You just need to calculate the input voltage rating and the output current rating. In this video, I will walk you through real examples and you will learn exactly how to get these two ratings right. To make this even easier, I coded a free calculator that does all the math for you, and it even links directly to charge controllers that match your system. And if you're using a PWM controller instead of an MPPT, I've also included a dedicated section in this video for that too, since the sizing process is slightly different. Let's get into it. Consider this MPPT charge controller from Victron. This number right here is its input voltage rating, the maximum voltage the controller can safely handle. In this case, it's 100 volts. Now, what actually happens if your solar array goes over that voltage? In most cases, the electronics inside the charge controller would take permanent damage. Best case scenario, if the controller has built-in overvoltage protection, it simply won't turn on, which means your batteries get zero power. But even then, there's no guarantee the internal circuitry is fully protected. To prevent all of this, you need to know the maximum voltage your solar panels can produce. So how do we figure that out? Let's start with the highest voltage a single panel can produce, the open circuit voltage, or VOC. For example, this Renogy panel shows a VOC of 22.5 volts. That's the maximum voltage that a single panel of these can produce. And you probably already know that if we wire panels in series, the voltages add up. So let's say we had 4 of these in series, the system VOC would be 4 times the VOC rating of a single panel. That's 22.5 times 4, which equals 90 volts. If we compare that to our Victron's 100 volt limit, it seems safe, right? Well, not necessarily, because here's the thing most people overlook. That VOC number is measured under standard test conditions, STC, and one of these conditions is a temperature of 25 degrees Celsius, or 77 degrees Fahrenheit. But solar panels don't operate at a fixed temperature, and the voltage they produce actually varies with temperature. The colder the solar panels get, the higher the voltage they produce. So on cold, sunny days, the real VOC of your panels can exceed the number printed on the label. Exactly by how much depends on the temperature. And that's where this table from the NEC comes in. It gives us the correction factors needed to calculate the actual VOC in cold conditions. Let's take Denver, Colorado as an example, where periods of clear, sunny, below freezing days are common. And let's assume that during these days, the temperature during daytime can reach minus 10 degrees Celsius or 14 degrees Fahrenheit. Using the NEC correction factor for that temperature range, our array's VOC could rise from 90 volts to 102.6 volts. Now we have a problem, because that number is above the controller's 100 volt limit. So we'd need a higher voltage controller, something like a 150 volt MPPT. However, that would be an expensive upgrade. An alternative solution that's cheaper would be to simply change the configuration of the solar panels. For example, if we wire the same panels in a 2S2P configuration, we would cut the maximum voltage in half, well under the safe limit. So to recap, to determine the MPPT's required input voltage rating, take the VOC of your panels, multiply it by the number of panels in series, then multiply it again by the NEC temperature correction factor. And if you already know the charge controller's input limit and want to find the safest configuration, use this formula. In any case, we're not done yet, because what we've covered so far is just about keeping your system safe. Now we need to make sure the charge controller can deliver every watt your solar panels generate. This is the output current rating of the solar charge controller. and it tells you the maximum charge in amps it can deliver to the battery. Now here's the problem. If the output current rating on your controller is too low, the current that your batteries get will be limited to that rated value, even if your solar panels could provide more. Additionally, the charge controller would be working at 100% most of the time, which means overheating, faster degradation, and shorter lifespan. In fact, to protect itself, a smart controller like this one will actually reduce the output current to reduce the operating temperature, which means even less current to the batteries. Then how do you find the right output current for your setup? Here's the key. An MPPT lowers the voltage from the solar array to match the battery voltage. And because watts equal volts times amps, when voltage goes down, amps must go up to preserve power. This is one of the advantages of MPPTs. They preserve power by converting the extra volts into usable amps. This gives us the following formula. Since we're solving for the output current, we simply need to divide the wattage of the solar array by the voltage of the battery. Let's use the same 4 solar panel array example as before, and let's say we're using them with a 12-volt battery bank. Since each of these solar panels is rated at 100 watts, no matter how they are wired together, the total wattage of the array will be 400 watts. Using our formula, this tells us that the output current rating of the MPPT needs to be 33.3 amps or higher. So a 40 amp controller like this Renogy Rover would be a good choice for the system. Now here's an important thing to add. If done right, your solar array can still be larger than what your MPPT is rated for to a certain degree, without harming the controller. In fact, this is called overpaneling, and in many cases it can be useful and more cost effective than using a larger charge controller. But I'll get to that in a couple of minutes. First, let's look at an example that combines both the input voltage and the output current calculations. For this example, let's scale things up. Say you have 8 of the 100 watt Renogy panels from earlier. That gives you an 800 watt solar array. Let's also say the array will be paired with a 12-volt battery bank made from 4 12-volt batteries wired in parallel. First, let's start with the output current rating, since it doesn't depend on how your solar panels are wired. 800 watts divided by 12 volts means we need a controller that can deliver 66.7 amps or more. This Victron MPPT is rated for 70 amps, so it meets that requirement. Now, let's look at the input voltage rating, because that determines how we can wire the solar panels. This controller is rated for 150 volts on the input side. Assuming the same panel VOC and temperature correction factor as the example from earlier, we can only connect up to 5 panels in series before exceeding that 150 volt limit. But we have 8 panels, so a 4S2P configuration works perfectly. 2 parallel strings, each with 4 panels in series. With this configuration and using Discharge controller, the system will be safe with enough headroom for production. However, there's actually one change that we can make that will allow for a cheaper option. All we need to do is simply change the configuration of the batteries and make it a 24-volt battery bank instead of 12 volts. This can be done by wiring the batteries in a 2S2P configuration. That's 2 parallel strings of 2 batteries in series. Let's run the formula again. At 24 volts, the required output current drops from 66 amps to 33 amps. So instead of having to use this 70 amp MPPT, we can now use this 35 amp MPPT, which costs less than half as much. But always make sure to check if the controller you choose is compatible with your battery bank voltage. For example, the 35 amp model I just mentioned works with banks from 12 volts up to 48 volts. Now, if you want an easier and much faster way to do all these calculations, I made a tool specifically for this and left a link to it in the description below. The calculator will determine your charge controller ratings, find the charge controllers that match these ratings, and provide direct links to those. All you have to do is enter a few key numbers: the wattage of each solar panel, the panel's open circuit voltage, your battery bank voltage, and the lowest daytime temperature your panels might experience. Then you simply describe your solar array configuration, how many solar panels you have in series and how many strings are in parallel. Following the example we've been using, I'll enter 100 watts, 22.5 volts, select 12 volts, and -10 to -6 degrees Celsius, and then enter 4 panels in series and 2 parallel strings. And as you can see, the calculator instantly gives us the required ratings and even suggests 2 charge controller models. This is very useful because you can tweak the numbers and immediately see how your system changes. For example, switching the battery bank from 12 volts to 24 volts lowers the output current requirement, and changing the array from a 4S 2P configuration to 2S 4P lowers the input voltage requirement. Now, before we move on to PWMs, there's one last thing that I hinted at earlier and I need to explain. Overpaneling is when you install more solar wattage than your charge controller can actually convert into output current. At first, that may sound like a bad idea, but it's actually a very common and cost-effective way to maximize system performance. Let me explain how. Solar panels almost never produce their full rated wattage. Even in great conditions, a 100 watt panel might only output 80 to 90 watts. And in the mornings, evenings, winter months, or on hazy or cloudy days, those numbers are much lower. So what some system owners choose to do is add more solar panels so that the array can produce more power in these less than ideal conditions. And the interesting part is they do this without upgrading to a larger charge controller. Since the solar panels have gotten cheaper over time, this helps increase the daily performance of the system at a relatively cheaper cost. For example, this is what the power production of a system with no overpaneling looks like in less than ideal versus in good conditions. And up here is the limit of what the charge controller can supply to the battery. Typically, this limit is almost never reached when the system is not overpaneled. Now, compared to that, this is what the power production of the system would look like with overpaneling. As you can see, when the conditions are not that great, the overpaneled system produces more power and makes better use of the controller's capabilities. And when the conditions are actually good, the system produces so much power that it maxes out the charge controller in peak sunlight hours. Whatever excess power the MPPT can send to the battery is simply clipped. But you still end up with more total daily energy than you would without overpaneling. So overpaneling can absolutely be worth it, but if you're going to do it, there are 2 important things you need to keep in mind. 1, higher stress on the controller during perfect conditions. On great sunny days, an overpaneled array pushes the MPPT closer to its maximum output. If that only happens occasionally, or if you're using something like a Victron MPPT which automatically reduces the output to protect itself, it's usually fine. But if your location gets days or weeks of perfect conditions, this can affect the controller's longevity. 2, there is a strict limit to how much you can actually overpanel. Some controllers clearly state this limit. For example, the 40 amp Renogy Rover allows up to 520 watts on a 12 volt battery bank and 1040 watts on a 24 volt battery bank. Other controllers don't give you an overpaneling wattage limit, but they give you the information you need to determine it. Take this 30 amp Victron MPPT. The manual specifies the maximum PV short circuit current. And because the input voltage rating is a hard safety limit, overpaneling usually means adding panels in parallel, which increases current. So the combination of the input voltage limit and the max short circuit current limit tells you exactly how far you can go. To make sure you're under the overpaneling limit, step 1 is to make sure your array's voltage stays under the controller's voltage rating using the same method we covered earlier in the video. Step 2, make sure your array's short circuit current stays under the controller's max PV short circuit rating. Start with the panel's rated short circuit current, multiply it by the number of parallel strings, and then multiply that by 1.25. This 1.25 safety factor accounts for scenarios where the panels receive more sunlight than the 1000 watts per square meter used in standard test conditions. So just as a recap, use this formula to determine the maximum number of solar panels in series, and use this formula for the maximum number of strings in parallel. Similar to MPPTs, PWM charge controllers also have an input voltage rating and an output current rating. And to figure out the required voltage rating, we use the exact same formula from the MPPT section. However, since PWMs operate differently than MPPTs, the current rating calculation for these controllers is a little bit different. Instead of converting the extra voltage into usable current like MPPTs do, PWMs decrease the voltage but keep the current exactly the same. That's why for a PWM, the required output current rating is simply the maximum current your solar array can produce. That's the short circuit current of one panel, multiplied by the number of strings in parallel, and then multiplied by the 1.25 over a radian safety factor. For example, let's say I have 4 of the same solar panels I used in our earlier examples. Now, most PWMs that I've seen have an input voltage limit of 50 volts. So we'll assume the same limit here and use that to determine the number of panels we can connect in series. These panels have a VOC of 22.5 volts. And earlier we used a temperature correction factor of 1.14. When we plug in the numbers, even 2 panels would exceed the controller's voltage limit, which means these panels can only be wired in parallel. So now we calculate the output current requirement. Each panel has a short circuit current of 5.75 amps, and we have 4 of them in parallel. With our formula, this gives us 28.75 amps. So for this setup, we can use this PWM charge controller from Renogy. It has a 30 amp output current rating and a 50 volt input voltage rating. That's it for this video. If you found it helpful, hit the like button and subscribe so you can get notified when I post more videos like this. If you have any questions, leave them in the comment section and I'd be happy to answer them for you. Thank you guys for watching and I'll see you in the next one.